and also the equilibrium of the body, that one. So today again, we are going to continue the same topic. We'll explore more number of numericals, the application part, what you can say now to it. So we have here on screen a question. A circular rope of weight W and radius R is resting on a smooth sphere of radius R. Okay, there's a small diagram they're given. That one. So almost rope is telling, find the tension in the rope. What is this? You may find a little bit difficulty with the diagram itself. I feel that one. So you can draw one circle. Okay, let this be the circle. Then a rope. Let me introduce a rope. This is center of circle. Rope, you have to show like this. Of course, it appears curved only. So this will be the rope here. See, once you have clarity of diagram, it's very easy. Then you can go for showing forces, then equating them. If the equilibrium, equate the forces. If it is the acceleration, then a net force F external equal to ma. This is a method you have to proceed here. See, once you gain confidence in laws of motion, no, the physics is over. I think you can stop coming to my class. That much I can say here. Very openly, I'm saying that one. Kinematics, you know, regarding the motion, all the different calculus involved in it. In laws of motion development, you are going to explore how to write the equations for the motion. I think the whole physics just revolves around only on these two ideas. So this will be the circle, no? Actually, the other side, we will not be able to see that. So if you are getting confusion, girls, or like you'll be having airband. So you take any apple or ball, anything, or tomato, that one. So you put that airband on that. And I'm going to ask you the tension in that airband. Fine, able to get out this. See, all these are not something very unusual. They are very usual things. So this is R. R is how much? So keep like this. Weight of radius R by 2. So what is smaller? Smaller equal to R by 2. So this distance will be how much? Capital R. Okay, let's take this distance as Y. Keep theta. Okay, now we'll define lambda. Some mathematics will take care of this. Let M be the mass of the W is what? W is what is called as mg. That one. You can take W.
Then
lambda is equal to m by 2 pi. What is the radius of this? Radius is r, so this will become m by 2 pi r by 2.
Sir, sorry sir, but what is lambda?
Linear mass density.
Okay, sir.
Every time lambda, linear mass density. So I'll define it here. Linear mass density of rope. So this will become m by pi r. Keep it like this here. So let's assume now what that rope will be in contact with that sphere, no? Rope will be in contact with that sphere. So here, let me assume a small element. Then how the weight of that will act here. dmg. Then what are other forces acting? Normal contact. If this is theta, this should be theta, no? I'm asking you to assume small element on the rope. It's all about how well you analyze the diagram, nothing else in there. So this is what that small element dm. So its weight will act like this, no? That's what I'm showing. Okay, got it? So the length of this, let it be dx. Now we will balance that weight DMG, vertical component of normal contact. Normal contact, don't write n, only at that particular point. No, for that small element, let it be dn. So we are discussing now the problem for only an element. So what do you mean by, sir, element? You draw small strip, length of dx, like what is a circle? Circle made up of arc, no? So that small element will have a mass dmg. That small element, the total ring will be, rope will be in contact. The small element, there the normal contact acting, let it be dn. So you equate now the forces. Now along y-axis, net force along y-axis 0. So dn cos theta minus dmg equal to 0. So you keep this equation, dn equal to dmg by cos theta. Keep it here. Now we will balance the horizontal component dn sin theta. Somebody should balance. So the tension in the rope. Sir, how the tension is set up? So again, we'll take the let this be the, I need one more circle. Okay, no. This is the center O and you call C. Is it okay? Then O is the center of the smooth sphere, that one. So here this is like a rope. Rope is what I'm showing here now. You are weaving from top. This is what top view. This is what side view. See, this is what you needed, a basic idea. You just take some ball, on that you put that rubber band, air band on that one. You can view from side. If side view, it will appear like this. If you view from top, top means like this. Fold it top like this. This is called like a side view, no? This will be like a top view. So top view, what you are going to see the rope, that one. So here you assume a small element. That small element, what we assumed here, no? So let this be this one. Okay, let's go for the mathematics. This will be, let this angle be phi. This is our small r, actually it is radius, no? Radius of the smaller. Now we will balance this dn sin theta. Is it okay? The small element. I'll write it here. Now who will balance anybody? The tension in the rope only. How the tension in the rope? Now, one more property of tension. Yesterday, what happened? We just made a few things. So how tension will act? Tension always will act tangential to the length of the string. This is one more property. Nobody asked this. I actually waited. Is anybody notices this, or how the tension will act as along the string? So nothing but, what is the definition? The tension will act tangential to the string, that one. So what do you mean by tangential? So you already you come across. I'll just put, I'll come back to the problem. So if this is a tension, if there's a rope, you take small element, how tension will act tangential. It will be like this. What about here? Along the length of the rope, it will act. If the rope is of this shape, tell me how you have to show tension. You have to show tension like this.